Hey everyone, today we're going to be moving on to Unit 3, Intermolecular Forces and Properties. This is the longest unit in AP Chemistry and it's also weighed the heaviest. So to start off for Unit 3, we're going to be talking about 3.1, Intermolecular Forces. So intermolecular forces are attractions between molecules. That's what we mean by inter versus intra, which means within. Inter means between molecules that help hold compounds together. So there are a few varieties that we're going to go over, but many physical properties reflect intermolecular forces, like boiling point, melting point, viscosity, solubility, and surface tension. Or the ability for a liquid to kind of hold on to itself and kind of not spill over. So liquid holding on to itself is essentially what surface tension is. And so these intermolecular forces affect all of these in some way, affect these properties. So these are the five main types of intermolecular forces, or IMFs, that we're going to be talking about in AP Chem. The first is London dispersion forces, which you also sometimes see called London dispersion. You can see up here on the right, these are sometimes called van der Waals. Forces or interactions. Right, and so if you ever see van der Waals interactions where they're talking about London dispersion forces. We have those dipole forces, dipole-induced dipole forces, ion dipole, and hydrogen bonding, which is a very special kind of dipole-dipole force that we're going to talk a lot about and see a lot. One thing to note that is, and I'm going to highlight this out in red, this is not an actual bond. I'll talk about this a little bit more when we actually get to it, but this is not an actual bond. It's just called hydrogen bonding. It's still a type of intermolecular force. So the first IMF that we're going to talk about are London dispersion forces, again, or van der Waals forces, as you might sometimes see them being called. These are caused by the motion of electrons within an atom or molecule. Right, we know from our previous unit and just previously from learning about chemistry that electrons are always moving around the entire atom or moving around the molecules. If it's a covalent molecule, for example, those electrons are shared and they're kind of being moved around. And so while they're moving around, occasionally they might end up on one side of the molecule versus the other side. And so if we look over at this diagram here on the top, we have no polarization, so those electrons are all kind of equally scattered around the entire atom. But let's have a scenario where after some time and movement, right, some electrons are on this side, right? So we have more E- on this side, and then on this side we have less electrons, right? They just so happen at one point to be on one side of the atom versus the other side of the atom. What will happen is that this side will have slightly more negative charge, and if you ever see these delta minus or delta plus, what that basically means is that it has a partial negative or partial positive charge. So I'm going to write down here, delta equals partial charge. And if you're wondering about the symbol, that is a lowercase delta or the lowercase Greek d. And so these, if you ever see these deltas, what it's saying is that there's a small amount of charge, either positive or negative, on one side, but it's not an actual full charge. And so when you have this slightly negative charge on one side, what's going to happen to atom B? Well, you have slightly positive, negative attracts positive. So again, after some time, right, the electrons from atom B are going to move close to this partial positive charge. And so now you have a little bit of an attractive force right there. Right? And so because you have that attractive force, these two atoms are going to kind of be slightly closer to each other, but they're not actually chemically bonded to each other. And you can see the same thing happens with molecules. If I have this molecule of H2, after some time, maybe one hydrogen has a few more electrons than the other hydrogen, right? It's a covalent bond. And then if you wait a little bit more time, the left hydrogen on molecule B will also have slightly more electrons and be attracted to the positive side of molecule A. Right, and so this is the result of Coulombic attraction, right? Coulombic meaning follows Coulomb's law, and it's present in all molecules. Right, and so if you ever are stuck on thinking of, well, what kind of intermolecular forces am I feeling in my molecule? Well, London dispersion forces will always be present. They're always typically also weak forces compared to other IMFs. Right, and so they're always present, but they're generally not the strongest one if you have any other IMF present. And another trend that's really important to keep in mind is that LDFs, right, London dispersion forces, increase as molecular weight, or MW, increases. So the higher molecular weight, the higher your LDFs. There are two other kinds of properties that also affect LDFs, or London dispersion forces. Those are polarizability and shape, molecular shape. Right, so polarizability is basically the ability to distort the electron cloud. So for polarizability, kind of to get a understanding of it, let's compare oxygen and sulfur. For oxygen, right, we have 8 electrons total, and those are present in 3 orbitals. And they're pretty close to the nucleus, right? Our largest orbital is 2p6, and so they're pretty close to the nucleus. For sulfur, we have 16 electrons, right? Sulfur is directly below oxygen, so the valence is still the same. You have 16 electron total. Those are present in 5 orbitals. Right, and your largest orbital is 3p6. And so the electron cloud of sulfur is much larger than oxygen, and so those electrons can move more freely. And they will respond more to distortion. And so as you kind of go down and you have larger and larger electron clouds, your electrons are more distortable, meaning they're more polarizable. So larger electron cloud, or just in general, more electrons and orbitals equals more polarizable. As for shape, longer / more surface area equals higher LDFs. Right, so the longer your molecule is, the larger it is, the more surface area it has, the more those electrons can be distorted. The next IMF that we're going to be talking about are dipole-dipole forces. And so these are forces between permanently polar molecules. What do I mean by that? Let's take acetonitrile, for example, in the example below and also drawn above. Right, if we look at our electronegativities for carbon, it's quite low, and for nitrogen, it's a little bit higher. And so the electrons prefer to go that way. And so the positive, this is kind of the more positive end, right, delta plus, and this is our more negative end. And no matter what for acetonitrile, it always has this dipole. And so that's what I mean by a permanently polar molecule. And what happens here is the opposite ends attract each other. Right, and so if we look at our diagram down here, we can see that this blue nitrogen here is attracted to this CH3 portion here of acetonitrile, right, which makes sense because nitrogen has these two lone pairs. Well, it has one lone pair, right? It has these two electrons. And so those electrons are going to be kind of attracted to that slightly more positive end of acetonitrile. And the same can be said about our repulsive forces, right? These electrons on acetonitrile from that nitrogen don't want to be near each other, and so they start pushing each other away. One trend to remember for dipole-dipole forces is that for equally sized molecules, or similar molecular weight, MW, boiling point increases as polarity increases. And so if you have a stronger dipole, as in those electrons are being kind of pushed towards one side of the molecule more than the other one, then your boiling point will go up as well. The next IMF is dipole-induced dipole, and so this is between a polar and a non-polar molecule. And so, for example, if we're thinking of O2, right, that is a non-polar molecule because it's equal on each side. There's an oxygen on one side, oxygen on the other, and so they're equally pulling on each other or pushing on each other. And then take something like H2O, right, which is polar. You have the oxygen, which is more electronegative. It's going to want those electrons. You have the hydrogens, which are less electronegative. They won't want the electrons. What will happen is if you have, say, a molecule of O2 near a molecule of H2O, right, we have our two lone pairs on O2, and then we have two lone pairs for the oxygen on water. What will happen is these electrons will kind of be pushing on the electrons there. And, right, of course, electrons don't like being near each other. And so, naturally, what will happen is the electrons from O2 will kind of want to go this way. And so we'll have a slightly negative charge there, and we'll have a slightly positive charge there. And as a result, right, because we have a slightly negative charge and a slightly positive charge, the slightly negative end of our water will be attracted to the slightly positive end of our now slight-induced dipole oxygen. And so if you have a polar molecule near a nonpolar molecule, what will happen is the electrons from the nonpolar molecule will move to one side, and then the more negative end of your polar molecule will be attracted to that more positive side of the molecule that you just created. So this is always an attractive force, and the strength of the IMF increases with polarity of the polar molecule and polarizability of the nonpolar. The next IMF that we're going to talk about is ion-dipole interactions. And so this is between a polar molecule, such as water, right, H2O, and some sort of an ion. And so if you have, for example, NaCl dissolved in H2O, you'll have some Na ions, some sodium ions, and some Cl ions, some chloride ions dissolved in that water. And so if I have my water here, what will happen is this cation, the sodium plus, will be attracted to the lone pairs of my oxygen, and the chlorides will be repelled by those, but then of course, right, our Cl minus will also kind of be happy around this slightly positive side of the hydrogens. And so you'll have this orientation, which is shown here on the right, where the hydrogens from water are going to kind of be pointed towards the Cl minus, whereas the oxygens from the water are going to be pointed towards Na plus. And so this is what makes ionic substances dissolve in polar solvents like water, and they tend to be stronger than dipole-dipole. They also just tend to be the strongest IMFs. The last IMF we're going to be talking about is a special sort of dipole-dipole interaction, and that's a hydrogen bond. And so once again, as a reminder, this is not an actual bond, right? And with any IMF, they're not actual bonds. They're just interactions, attractive and repulsive forces between molecules, but they're not actually bonded to each other. And so hydrogen bonds are not actual bonds. And so this is attraction between hydrogen atoms attached to oxygens, nitrogens, or fluorines to another oxygen, nitrogen, or fluorine on another molecule. Right, and so what do I mean by that? If we look at this, this little diagram here on the right, you have water, which has hydrogen bonded to oxygen, and you have another water molecule, hydrogen bonded to oxygen. You'll have this sort of attractive force between the electrons on the oxygen of one water and then the hydrogen that's on your other water molecule. You'll see the same thing with HF, and so you have your electrons here on the fluorine of hydrogen fluoride. That'll be attracted to the hydrogen on another hydrogen fluoride. Same thing with nitrogen, and this can happen between different molecules as well. And so you'll have the hydrogen that's covalently bonded to our oxygen on water. That's going to be attracted to the nitrogen on our NH3, our ammonia. And the reason behind this really has to do with electronegativity, right? We have really high electronegative elements. Nitrogen, oxygen, and fluorine are all the way towards that top right part of the periodic table. So electronegativity is high. The electrons are going to want to go towards that more electronegative atom. All right, and so here you have hydrogen, that's going to be your slightly positive location. Oxygen, nitrogen, or fluorine, that'll be your slightly negative location. Although in the case of hydrogen, right, because it has no other electrons, you basically have almost no electrons going towards that hydrogen, and most of them are towards the oxygen. It's still a covalent bond, right? It's not completely ionic, but those electrons tend to want to go towards the more electronegative atom, and so that's why we have this special bonding, or this special interaction with hydrogen. So if we're thinking of all the IMFs together, right, because these don't exist on their own, they all exist together, we can kind of look at all of our different groups of substances, atoms, nonpolar molecules, polar molecules without OH, NH, or HF groups, polar molecules that have those groups, and then ionic solvents, solids dissolved in liquids like sodium chloride dissolved in water. We can think of all of our different interactions. For dispersion forces, right, I had said on that slide, these exist in every single type of molecule. They're always going to be present. And so if you're wondering how many total IMFs are in a molecule, dispersion forces should always be there. There should always be at least one IMF in any molecule that we're studying. For dipole-dipole interactions, these only exist in molecules that have permanent dipoles. Atoms and nonpolar molecules are not polar. They do not have permanent dipoles. Polar molecules, of course, do. And then polar molecules that contain OH, NH, or HF, of course, obviously do as well. And so dipole-dipole interactions will only be in polar molecules. For hydrogen bonding, right, that is a dipole-dipole interaction, but that is especially only in molecules that have this OH, NH, or HF groups present in them. And then finally, ion-dipole interactions, those will only be present when you have some sort of an ion dissolved in a polar liquid, like sodium chloride, like potassium carbonate, like any other salt dissolved in something like water. right? And then the energies are also here. We have our dispersion, our LDFs, London dispersion forces. Those are always pretty weak. We have dipole-dipole interactions, which can be pretty weak and can be somewhere in the middle. Hydrogen bonding, which is typically a very strong dipole-dipole interaction. And our ion dipoles, those are the strongest interactions that we see. And so I'll just end off with a few trends that we see here with IMFs. The first is vapor pressure, which if we're not familiar with vapor pressure, if you essentially have, let's say, a little beaker with some water in it, some of it is liquid and some of it is gas. It's the pressure that the gas exerts on the liquid. So it's the pressure coming down from the gas on that liquid. As IMF, any IMF increases, vapor pressure will decrease. For boiling point, right, as IMFs increase, boiling point, or BP, will also increase. Melting point, as IMFs increase, your melting point will also increase. We'll go over a little bit of practice in class, but for now, that's it. Thanks, guys.